Assalamu alaikum dear students. We are in second lecture of week 4 for our engineering materials course. We were talking about atomic bonding and forces that keeps atoms and ions together. How these atoms or ions interact and how their mutual interaction results in energy and force and keeps these atoms in these atoms or a material in the form of solids, liquids or gases, and what other information we can extract from energy and force versus interatomic diagrams, like their modulus of elasticity or coefficient of thermal expansion or their solid, liquid or gaseous state or melting temperatures high or low. Now we will study different types of bondings that are found in solids that keeps these atoms or ions together in the solid. There are two general categories of bondings. One is called primary bonds, second is called secondary bondings or secondary bonds. Primary bonds are chemical bonds, are found in solids, and these bonds have three types. These are ionic, covalent and metallic. These bondings are a result of electronic structure of atoms and involves necessarily or actually valence electrons. As we know and have discussed earlier, that atoms tend to remain in lowest possible energy states, or ground state, or so to speak, stable state. These bondings are therefore the result due to tendency of atoms to assume stable or complete electronic structures, so to be in the lowest possible energy states. And the other type or category of bonding, that's called secondary bonds. Again, there are hydrogen bonds, polar bonds. We will be talking about in the next couple of slides. These secondary bonds are actually physical bonds. They are weak in energy or force in comparison to primary or chemical bonds, and these secondary bonds result due to position of atoms or ions within a material. These bonds influence physical properties of solids. So in the next slides, we will talk a little more about these primary and secondary bonds and their types. Within them, their types one by one. Moving on to the next slide, starting with primary bonds, we first talk about ionic bond. This bonding is found in compounds of metallic and non-metallic elements. In this bonding, we will have complete transfer of electrons. That is, from one atom to the other atom, electrons are completely transferred. They move into the structure of the other atom. In this case, and in this process, after this process, actually the transfer of electrons process, both the atoms will have their outer shells filled. So they will have filled outer shells, so they will become inert, as to speak, and they will get stable, as we were talking before, that atoms come into bondings to get into the stable states or lowest possible energy states. Of course, we know electrons carry negative charge, so their acquisition or release results in negative and positive charge respectively for the atoms to which they go or from which they go. This bonding is actually complete transfer of electrons, so this bonding is non-directional. It means in every direction we will have the same amount of bonding energy existing between these two atoms. Okay, so this is why this is called non-directional bonding. It means independent of the direction they will have the effect of the bonding. This figure 2.11, an example of sodium chloride, wherein sodium releases an electron and chlorine acquires an electron to get their electronic structure filled or outermost shell filled, and they get an inert state and become in bonds. And as both the atoms have their outer shells complete, so this bonding results in non-directional bonding. In every direction, the effect of the bonding will be the same. And figure B shows us the Coulombic, Coulombic bonding forces that exist between sodium and chlorine. Because of this acquisition of or release of electrons, and in the result and resultingly acquisition of positive or negative charge by releasing and absorbing or acquiring electrons. So, in this process, of course, sodium releases an electron, so gets positive charge due to loss of electron, and chlorine acquires an electron, becomes negative charge because of this acquisition of electron. We move on to the next. Here we will talk about in ionic bonding, we will get attractive Coulombic bonding forces because one is positive, the other is negative. Attractive energy, as we have already studied, is function of interatomic distances. Okay, and in this case, this attractive energy is more if separation is small, and this attractive energy of course will be low if separation is higher. So attractive energy is minus of A over R. We keep it minus just to distinguish it from the repulsive energy. Okay, this A is a constant. Do not confuse this A with atomic number, atomic mass. This is a constant and it is determined experimentally, and it carries generally a relation that is 1 over 4 pi epsilon naught. Constants Z1E, Z2E. E is the electronic charge, and Z1 and Z2 are absolute values of valences for the two ions, that and E is electronic charge. Remember again that C here is not usual atomic number. A is not atomic mass, C is not atomic number, but A is constant that is determined by this formula, and in this formula the Z is number of valence electrons for the two atoms in the bond. So Z1 for example for sodium and Z2 for chlorine. In this case Z1 and Z2 is 1 for both of sodium and chlorine. Okay, this again the repulsive energy relation that we result because of this bonding is a B over Rn. Again here B and N are constants, and it's the value of these depend upon ionic system, and it varies from one to other ionic system. Here I will suggest you to please check problem 2.2, wherein they explain about this ionic bonding and calculations of this attractive and repulsive components, and also the character of the ionic character of the bonding, and we can then discuss this example during our live session. Okay, we go on to the next slide, and we will talk about the second type of primary bond, that is called covalent bond. In this bonding, valence electrons are shared among participating atoms to complete outer shells for stable configurations. Okay, in the first case there was transfer of electrons, and in this case there is sharing of valence electrons. Each element shares electron, and shared electrons belong to both atoms, as in shown in figure 2.1. In case of hydrogen, divalent hydrogen or H2. This figure shows covalent bonding in molecules of hydrogen, H2, As you can see in the figure, bonding exists emphatically, that is more strongly along the direction of shared electrons. So the bonding is along the direction that is in between these two atoms, as you can see on the right side of your figure. More strongly, more emphatically is present on the side of the where the electrons are shared. It means covalent bonding is directional in nature because it will be along the direction of shared electrons. As this bonding results because of sharing of electrons, atom with greater number of shared electrons shares these combined electrons for longer times. So these shared electrons will remain towards the side of the atom that have shared greater number of electrons in the bonding. So covalent bonding is sharing of electrons. As this is sharing of electrons, covalent bonding more forcefully exists along the direction of sharing. So it is a directional bonding, and this shared electron will remain towards the side of the atom that has shared more electrons for longer times. We move on to the next, that is the third type of primary bonding, that is called metallic bonding. As the name suggests, this is found in metals and their alloys, and this third class in primary bonding called metallic bonding is found in metals that usually have valence electrons that are assumed to free. So in metals we assume, or practically, the electrons, the valence electrons are taken as free electrons. Free means that they can move around within their structure, within that material boundaries freely. And it appears like this, that they are like the atoms of the gases. So just like those atoms of gases which can just move around freely, we take these electrons as free electrons. So they exist in the form of electron clouds or sea of electrons. And these are free to wander around about within the matter or element. So these electrons are not taken as associated or bound to a particular just one atom. So they are not taken as an electron of that particular atom, but they are taken on the whole as sea of electrons, as such that they are free, and they make another group of you can say constituents. So they are taken as belonging to the metal as a whole, not just one atom, but overall to the metal as a whole. These electrons are therefore taken as we talked earlier, are called as electron clouds or sea of electrons. And these electrons carry negative charge. So this sea of electrons or electron clouds is taken as a negative charge, and the remaining core are the nucleus and the shells, which are complete in their structure. They are complete with the number of required or permitted electrons. They are taken as a positive charge. So negative and positive, two opposite charges. So they become in Coulombic interaction, and these form a bonding as a sense. Positive charge, the core electron, the nucleus with complete outer shells, and the valence electrons, they become in contact. An iron core, positive charge, electrons, negative charge, so they make the bonding. Because they are equal in charge, but opposite in charge, one is positive, another is negative, so there results attractive force or attractive bonding in between this ionic core and the sea of electrons. So these get in Coulombic interaction. Their Coulomb force that appears in between these sea of electrons and their ion core. And again, this is over the whole material or the matter structure. Again, this bonding is non-directional because it exists in every direction. So in the first, we have transfer of electrons, ionic. In second, we have sharing of electrons are covalent, and in this metallic bonding we neither have sharing nor the transfer, but the electron clouds that are valence electrons are taken as free and they constitute the negative part, and the ionic cores are the nucleus with filled outer shell, they are taken as positive. So these two constituents get in contact and form a bond that is called metallic bond. In this figure 2.19, of course, you can see that we have ion cores. Ion cores means nucleus plus the shells that are complete in their electronic structure. They are taken as positive, and the free electrons, so to speak, that is the electron in the valence shell of each and every atom that are not particularly bound to that particular atom, but they are free to move. They constitute another, so they become in between groups in the form of groups, positive and negative, and so they develop a sort of attractive force, that Coulomb attractive force, and get into a bond. And that is present over the whole metal, inside the whole metal from one side to the other. So this is again non-directional metallic bonding type. Now we move on to the second category, that is called secondary bonding, and these are also called van der Waals bonding. That already we talked about, that these are actually because of position of the atom. So these exist, these are physical bonds, and they arise because of particular position of the atom at one time. And these can exist in addition to the primary bonds. Of course, they are weaker in their bonding, in their strength, so they are not as apparent in the presence of primary bonds, but they do exist and they affect physical properties of the material. So these arise because of the atomic or molecular dipoles that are existing in materials, or they arise because of some external effect, as we will study in the next couple of slides. And this bonding that already we talked about results because of Coulombic attraction that develops between positive and negative portions of that. So they are actually overall a positive negative presence. They don't acquire a charge, overall charge, okay? Remember this. This is just because of the position of their internal negative and positive charge. Overall they may be neutral, okay? They don't get charged. But this is the presence of positive and negative charge at some particular time, at some particular position, that results in secondary or van der Waals bonding because of this separation or alignment of positive and negative charges. And again, this interaction is between positive and negative charge, and that will be in a particular direction where this alignment exists. So this secondary bond is directional in nature. It will be along the side where this positive and negative alignment is existing. In this, just in this figure 2.20, you can see that we have two atoms. Overall they carry equal charge, positive negative, positive negative. But now at some time, because of their position, the negative charge gets in proximity with the positive side of the other atom, of the other that has developed. So they have developed a positive and negative dipole, and they become an interaction. Coulombic interaction or force arises and they get into a bond. And that is actually only along this side where this positive and negative alignment exists for these two atoms. For example, hydrogen bonding is a special type of secondary bonding in molecules with hydrogen as constituents. These different sorts of secondary bonding because of dipoles in the case of hydrogen and other elements and materials are are shown in the next couple of slides, and you will see, you will observe by yourself that it is actually the physical position or alignment of the atoms that results in positive and negative dipoles, and these then result in interactions or Coulombic forces arising because of these positions and gives rise to the bonding types. Just like in figure 2.20, which shows the polar arrangement of positive and negative charges and how their physical arrangement results in van der Waals or secondary forces. They are not transfer or sharing of electrons, it's just the arrangement or the alignment of positive and negative charges that results in secondary bondings. Here in this figure you can see fluctuating induced dipole bonds, that we have a material or an element or an atom where we have nucleus and the electron cloud, positive and negative charge in figure 2.21a, and when this dipole comes in contact with a symmetric, electrically symmetric atom or molecule that has again a positive and negative charge, but because of this in figure B on the left side you can see a dipole which has an alignment of positive and negative charge, and this comes in contact with electrically symmetric atom or molecule which again has a positive and negative charge, but this now on the dipole on your left in figure 2.21b, because of its alignment the negative charge on the right side will attract the positive towards itself and repel the negative on the other side. So on the right side on the figure 2.21b you will see that the dipole that was existing positive and negative, it has attracted towards itself the positive side of the element or atom and repelled the negative side. So this again has resulted in another induced dipole. That's just like you have induced charge. If you remember the examples of how the bodies are charged, how bodies are separated in their charges. When you bring some charged object to another to the into the proximity of another element or matter, and it attracts positive or opposite charge to itself and repels the similar charge to the other side. Again, here a dipole that was positive and negative in 2.21b on your left comes into the proximity of electrical symmetric atom that again has a positive and negative charges, and then it attracts positive charge to itself and expels negative charge, and in figure B on the right side, the right down corner, you can see that one dipole has resulted in another dipole, and this positive and negative charge then gets into interaction or attraction, Coulombic attraction, and then one dipole has induced another electrical symmetric atom or molecule had dipole in it, and these two dipoles, because of their alignment of negative and positive charge, result into an secondary type of attractive bonding. And another example for the same is here polar molecule induced dipole bond. Here you have a molecule that is polar. See hydrogen and chloride, positive and negative. They are again positive and negative poles, and this gets in figure A, and now you take on to the figure 2.22b. In the figure 2.22b on the left side is this dipole, that is polar molecule with positive and negative charge alignment, and it gets into proximity of electrically symmetric atom and molecule, just like in the earlier example. This chlorine is negative and it attracts the positive charge in the another electrically symmetric atom or molecule towards itself and repels the negative charge to the other side and the opposite side, and this polar molecule then induces a dipole in the electrically symmetric atom or molecule, and again this dipole becomes positive or negative alignments into this form of dipole, and this positive induced positive side gets into the attraction of this chlorine side and they form a bond. Again you can see that this is because of the presence or the position of these two dipoles, and this secondary bond is actually existing along this direction only. That's why it is called directional bond because it exists only in the direction where the positive and negative charges of chlorine and induced dipole get into the alignment or proximity. Okay, if we can go to another example again, that is of permanent dipole bonds, that here again you have hydrogen and fluorine. Okay, hydrogen bonds, this again positive and negative, they get into the proximity and they exist for permanent bonding. Permanent bonding, it means that they are permanently there, so they have a secondary bond, that is because of their already existing dipoles, so they make a permanent bond. These were the basic two categories, and in these two categories different types of bonding. Again, as we talked earlier, we can have in one particular material mixed of bonding. We can have ionic covalent present at the same time and primary and secondary bondings present in a material at one time. These molecules, yes, like H2, CO2 and so on, they also make sort of bondings. This bonding type actually results are is, you can also take it as a factor for classification of materials. If you read the material I uploaded on LMS, you will get to know how this bonding type could be related with materials classification. So please go to that side of the reading material and write on a one single page how what type of material bonding will result in different types of materials. I mean, ionic bonding results in ceramics or polymers, composites, or metals, and how the covalent bonding usually results, that is whether it is in the ceramics that have covalent bonding, or it is composites, or it is metals. Okay, so please just go read this reading material given for or provided for the week 4, and you will get an idea from there that what different bonding types could exist for different classifications of materials. So this is your like an assignment, write on one single page. You can easily find this and write. Okay. Okay, here we finish, and we will meet inshallah after the your mid semester exam. Good luck for the exam, and see you later. In the meanwhile, I will prepare a lecture, a slide on the numericals or problems for this week 4, and I will upload, and then we will discuss this when we meet again after your midterm exams. Okay, Assalamu alaikum. Goodbye. Thank you.